Welcome to the lecture series on CFD, Part 2. This is lecture 36 on coupled simulation of flow and motion of flying and floating bodies. This lecture deals with simulation of flows involving bodies whose motion is not prescribed but is driven or significantly affected by flow-induced forces. We first describe the equations of motion for a rigid body subjected to fluid flow and external forces. Next, discretization and solution methods for these equations are presented, followed by a description of the coupled solution method for flow and body motion. One of the most important aspects of such simulations is the adaptation of computational grid to body position and orientation as it moves. 4 approaches are described: moving the whole grid as a rigid body, moving grid blocks region-wise, using grid morphing, and using overlapping grids. Advantages and disadvantages of each approach are discussed. Finally, 4 application examples are presented: patrol boat in calm water, container ship in waves, lifeboat water entry, and a boat maneuvering in waves. Simulation of flows around rigid bodies whose motion is prescribed was dealt with in lecture 26 on discretization methods for moving grids. Coupled computation of flow and flow-affected motion of rigid bodies will be discussed in this presentation. In engineering practice, multiple bodies may be connected by rigid or flexible structures, for example, catenaries, bars, mooring lines, etc., involving coupling elements like revolute joint, spherical joint, etc. Some commercial CFD software, like Simpson Testasis CM+, allows simulations involving various arrangements of multiple connected bodies moving in a fluid flow. This will not be dealt with in detail in this lecture. Bodies moving in a fluid flow may significantly deform due to flow-induced forces. This will be dealt with in lecture 40 on fluid structure interaction. Motion of a rigid body is affected by forces and moments acting on it. Gravity is a body force that is always present. External forces, for example, resulting from towing, propulsion, mooring, etc., may also be acting on the body. Flow-induced forces are also always present. Pressure force, acting normal to body surface, and shear force, acting tangential to body surface. This is illustrated in this figure, showing a partially submerged rigid body floating in water. P denotes the pressure, T is the tensor of viscous stresses, G is the gravity vector, M the body mass, R the position vector, and N the unit vector normal to body surface. C is the center of mass of the body, and V and omega are the linear and angular velocity of the body, respectively. The forces acting on the body are given by this expression. I is the unit tensor, and Fx is the resultant external force. To obtain moments of forces acting on the body, we need to compute the vector product of each force with the vector connecting the center of mass with the force action point defined by the position vector r. With the resultant force and moment determined, we can express the equations of body motion with 6 degrees of freedom, free linear and free rotational motions as follows. V is the linear velocity vector at the center of mass, M is the tensor of moments of inertia of the body in the global coordinate frame, and omega is the angular velocity vector at the center of mass. Moments of inertia in the global coordinate system would have to be recomputed every time the body orientation changes. This is too complicated for non-trivial geometries. Equations of rotational motion are therefore usually solved in a body fixed coordinate system where the moments of inertia of a rigid body are constant. Equations then change to account for the motion of the reference frame. MB is the tensor of moments of inertia of the body in the body fixed coordinate frame. When equations of body motion described in slide 6 are solved coupled with fluid flow, no added mass is used. The concept of added mass is needed only when the flow effects are indirectly accounted for via drag and lift coefficients. Other effects like Safman or Magnus lift forces also do not need to be added explicitly. They all result automatically from the integration of pressure and shear forces over body surface. The equations of body motion must be integrated twice to obtain the new body position defined by the position vector r and the orientation vector omega. This is usually done using the same integration method that is used to compute the unsteady flow, or at least using a method of the same order. For example, for linear motion, we first need to compute the velocity vector at the new time level from the equation of motion, and then the new position from the definition of velocity as the derivative of r. Here, time integration is performed by trapezoid rule, that is the Crank-Nicolson method. The subscript n denotes the new time level, while the superscript m stands for outer iterations within new time step. The new orientation is determined in a similar way. The new angular velocity vector is obtained from the second equation of motion from slide 6, and from this expression, the new orientation vector is computed. As shown in the preceding slide, one obtains first the new linear and angular velocity of the body. The second integration delivers the new position and orientation. Because the problem is coupled and nonlinear, an iterative solution method must be used. At the new time step, one first estimates the new flow-induced forces for the unchanged body position. With this estimate of fluid forces, an estimate of the new body position is computed. The grid in fluid must be adapted to the new body position in every step. There are many possibilities. Some will be described in slides 13 to 18. A new estimate of fluid forces can now be computed for the new body position. The process is repeated until changes in position and forces become negligible. This figure shows the flow chart of the iterative solution method. Computation of body motion is integrated into the outer iteration loop for flow computation, which is needed anyway due to the nonlinearity of equations. In the case of connected multiple bodies, equations for connectors are also solved within outer iterations. Not all 6 degrees of freedom are always considered. For example, ships are often only allowed to heave and pitch, assuming that other motions are negligible. The coupling within outer iterations is essential for the robustness of the solution method, especially when light bodies are moving in heavy fluid. With a coupled solution of flow and body motion equations, large time steps can be taken if accuracy allows, or if time accuracy is not important, for example, when marching towards a steady-state solution. Under-relaxation can be applied to both changes in body forces and moments from one outer iteration to the next, and to changes in body position from one outer iteration to the next. Under-relaxation in equations of motion for rigid body acts as an added mass, but when iterations converge, the effect of under-relaxation vanishes. Implicit coupling of fluid flow and body motion within outer iterations is important. Explicit coupling, that is, solving for fluid flow and body motion one after the other, usually leads to severe stability problems. Consider a sphere with density of 1 kg per cubic meter submerged underwater and let loose. In the first time step, fluid is at rest, so only the gravity and buoyancy forces act on the sphere, leading to this equation of motion. The result is an extremely high upward acceleration amounting to 999 gravity accelerations. This leads to too large displacement of the sphere. In the next time step, too large a fluid force in the opposite direction would result due to water resistance to sphere motion. The simulation would diverge. The greatest challenge is the adaptation of the grid to body motion. Because this needs to be done in every outer iteration within each time step, the method should be efficient. There are several options. Motion of the whole grid with the body without deformation, that is, the grid moves like a rigid body. Grid morphing. Near body, grid is deformed so that grid nodes originally on body surface stay there and the rest of the grid follows by deforming like an elastic body. Splitting of solution domain into 2 regions. One translates and rotates with the body, the other either only translates or is morphed. And using overlapping grids. One grid is attached to body and moves with it, while the background grid is attached to environment. It may be fixed or moving. The whole grid can be moved with the body if it moves in an infinite environment and no interaction with other bodies is present. For example, ship in ocean, airplane in atmosphere, etc. Mesh morphing is a good choice if motions are of limited extent. For example, ship in waves or ship in shallow water, performing only small translations and rotations, that is, heave and pitching motions. Otherwise, grid quality may become poor. The most flexible approach is to use overlapping grids, also called overset grids. See lecture 27 for details. The advantages of this approach are: multiple bodies can move relative to each other, including path crossing. Arbitrary body motion can be accounted for example, ship capsizing, lifeboat launch from a vessel or a platform, including overturning upon water entry, etc. And grid quality does not suffer when the body moves over a large distance. An example in which the motion of the whole grid attached to the moving body is possible is the simulation of lifeboat water entry. However, only when the free surface is flat. This plot shows surface grid on the whole solution domain, while in this plot a zoom around the lifeboat is shown. As the lifeboat is falling through the air, it accelerates and may also rotate. Viewed in a coordinate system attached to the lifeboat, the free surface propagates through the grid toward it. Initially, the free surface is not sharp because the grid is coarse, but it becomes sharper as it enters the finer grid zone near the lifeboat. Free surface will not be well resolved far from body because the grid remains coarse there and is not aligned with the mesh, but that is, in this application, not important. If waves were propagating along free surface, this approach would only work well if the grid was fine enough to resolve the wave propagation at all times, which would require a fine grid in the whole zone below the lifeboat. This would also not be a good option for a ship in waves because as it pitches, the grid at larger distance moves over a wider zone, and to capture the free surface and waves, the grid will have to be fine in a larger region. To increase the flexibility and avoid fine grid in a larger zone, one can split the solution domain into two regions. One region is attached to the body and moves with it without deformation, performing both translation and rotation. The other region performs only translation motion. In the example of lifeboat water entry from the preceding slide, assuming translation in x and z direction and rotation around y-axis, one can fit the lifeboat into a cylinder with a sliding interface to the blue grid shown in this plot. The blue grid is aligned with free surface, but it still needs to be refined in vertical direction in a larger zone so that the free surface remains within the fine grid as it translates up and down. Motion of a ship in waves that has the same 3 degrees of freedom could also be performed in this way. The third option for grid adaptation to a moving body is morphing. Two examples are shown in these animations. On the left, we see adaptation of grid to two rigid bodies moving in an enclosure relative to each other. On the right, we see the adaptation of grid to a deforming body. This approach is suitable when the motion is of limited extent, ensuring that grid quality will not severely deteriorate during morphing. Especially body rotation over a large angle is critical. The other problem is that grid morphing usually requires solving additional equations to compute the coordinates of grid nodes at each outer iteration, which may considerably increase the computing cost. The most flexible approach to grid adaptation to a moving body is to use overlapping grids. See lecture 27 for details about overlapping grids. Coming back to the example of lifeboat water entry, we need two grids. One is attached to the body and moves with it without deformation, and the other is attached to the environment and is fixed. It could also move if needed. The two grids can be of a different kind. For example, as shown in this plot, the overlapping grid attached to the lifeboat may be polyhedral, while the background grid may be Cartesian. The background grid needs to be refined around free surface and to some extent to match the size of the outer layer of the overlapping grid region in a zone within which the offset grid will be moving. This can be done in an adaptive way, following body motion, as will be shown in lecture 38. This plot shows active cells in both overlapping and background grid. The free surface was assumed flat. When wave propagation needs to be considered, the background grid must be refined to allow circa 20 cells per wave height and 80 cells per wave length. Because the background grid does not move, this is much more favorable than in previously described approaches. Let us now have a look at some application examples. The first example deals with simulation of flow, resistance, trim and sinkage of a patrol boat, performed at the towing tank facility Brodarski Institute in Zagreb, Croatia. The boat has 2 degrees of freedom, heave and pitching motion. Simulation was performed using SimSynthesizer Plus software and a trimmed grid locally refined around the boat with 3.4 million cells for a half of the flow domain, using symmetry condition in the midplane. The boat was first held fixed for a while, waiting for the flow to develop from initialization with a constant velocity of 30 knots. It was then allowed to pitch and heave. The animation shows how the resistance, pitch, that is the trim angle, and heave, that is the sinkage, converge to a constant value. These 2 plots show details of the grid and volume fraction of water in the longitudinal and one cross-section. The lower plot shows pressure distribution in the cross-section. The location of maximum pressure zones is related to the maximum curvature of the free surface. This high pressure zone forces water to turn and flow up along the hull surface, creating a layer of high-speed flow at atmospheric pressure. These wall-bounded plane jets are diverted by this step on the hull, as can be seen in the animation. These 2 plots show comparison of simulation results and experimental data for resistance on the left and for trim and sinkage on the right. Experiments were performed at the towing tank of Brodarski Institute in Zagreb, Croatia, after simulations were finished. The displacement fruit number is defined with the length expressed as the cubic root of the displacement volume, and u is the boat speed. Resistance, trim and sinkage obtained in experiments agree well with simulation both qualitatively and quantitatively over the whole range of displacement fruit numbers. Discrepancies are everywhere within measurement uncertainty, indicated by these bars. It is advisable to always perform simulation before doing experiments. This helps to identify critical feature and better prepare the experiment, including the choice of instrumentation and distribution of measurement locations when field measurements are performed. The challenges are greater when waves are present at the free surface. This animation shows the motion of a real ship in a rough sea. The additional complication here is the modeling of short crested waves. They are 3-dimensional with random components in both direction and phase. They can be generated by superposition of linear waves, but this is a separate topic. This and the following 2 slides are devoted to the simulation of flow and motion of a container ship model in long-crested Stokes waves. The aim is to determine the wave eddy resistance. The solution domain is circa 3.3 wavelengths long, and the ship model length is approximately equal to the wavelength, 7.5 meters. Ship speed is 1.2 meters per second, the wave period is 2.184 seconds, and the wave height is 0.2 meters. Both the initial and the inlet boundary conditions are defined by the Stokes fifth-order wave theory. To keep the solution domain small, the solution was forced toward the Stokes fifth-order theory in a zone 5 meters wide along inlet, outlet and side boundary. The hull is free to heave and pitch, and only 1/2 of flow domain was considered using symmetry condition in the midplane. Offset grids are used, and only the grid attached to hull moves. A wider refined zone near bow and stern is generated to accommodate pitching motion, that is, to ensure that the free surface remains within the fine grid at all times. Note also that the grid has the same spacing in x direction everywhere to resolve the wave propagation as accurately as possible without disturbances due to mesh changes. Away from ship, the grid is coarsened in y direction because waves are long crested. These animations of ship motion in waves show hull-induced disturbances to the regular incoming wave. Disturbances propagate in all directions, and the angle of hull-induced waves is larger than the Kelvin angle in a calm sea, which is theta equal 19.47 degrees. Because the nonlinear Stokes free-water wave satisfies the Navier-Stokes equations relatively well, the solution is forced toward the theory at inlet, side boundary, and outlet. See section 13.6 in the book for details about this method. This ensures that disturbances do not reach the boundary and reflects there back into the solution domain. These plots show the variation of resistance, lift force, and pitch and heave motion over 6 wave periods. After circa 5 wave periods, a periodic solution is obtained. Note that the encounter period is smaller than the wave period because the ship moves against waves. This is why we see 8 wave encounters in these plots. The shear drag does not vary much, but pressure drag varies with amplitudes higher than the mean drag. Over a part of encounter period, pressure drag is negative, that is, the ship is being pushed forward rather than opposing its forward motion. Note that in reality, ships do not move through waves at a constant speed, as in this simulation, but with constant power. In that case, the speed varies and the resistance oscillation around the mean value is less pronounced than in the case of an imposed constant speed. The third example is the simulation of water entry of a lifeboat using overlapping grids shown in slide 18. The lifeboat is dropped from a height of 32 meters into calm water. The angle at which is the lifeboat released should ensure that it does not dive too deep into water. It should resurface as soon as possible, switch its own propulsion on, and move away from the danger zone. However, the aim is also to ensure that deceleration during impact onto water surface is not too high. People inside should survive the drop. Therefore, compromises have to be made. These plots show the position of the lifeboat and the pressure on its surface at different stages of its water entry and resurfacing. Note the position of pressure maximum during water entry. It is always in the vicinity of the free surface. A large air cavity is formed behind the boat. The animation shows the motion of the lifeboat during free fall and water entry, the pressure on its surface, and the contour of the free surface in the symmetry plane. On the right hand side are photographs from an experiment performed by Norsafe in Norway. In both simulation and experiment, the lifeboat jumps out of water after resurfacing. This will be visible in the plot of accelerations on the next slide. Note in photographs large zones of water-air mixture, which cannot be properly modeled by the VOF method. But because they are behind the hull, the predicted forces acting on the boat and its motion are not significantly affected. These two plots show comparison of predicted and measured accelerations in the front, on the left, and the rear, on the right, region of the lifeboat, normalized by gravity acceleration g equal 9.81 meters per second squared. Upon impact onto the water surface, the front decelerates by 5g, while at the same time the rear part accelerates by 3g because the boat starts rotating around the slowed down bow. Once the stern hits water, the rear part of the boat decelerates by 6g. Considering that it has shortly before accelerated by 3g, the total deceleration is 9g, which is already at the limit of what humans, like trained fighter pilots, can survive if it does not last long. Another mild deceleration is encountered when the lifeboat jumps out of water and then lands on the water surface again, as seen in the animation and photographs from experiment in the preceding slide. The agreement between simulation and experiment is relatively good, considering that for this simulation a relatively coarse grid was used. See slide 18. The videos in this and in the following slide were contributed by Flavio Simolin and Miles Wiele from Siemens. They demonstrate how one can present multiple results in one animation to enable better understanding of flow features. The left video shows how a fast boat accelerates to full speed and moves in head waves. The video on the right shows the same information for the straight motion in oblique waves. In addition to free surface elevation and boat motion, included are also synchronized diagrams which show the variation of heave, pitch and roll motion. Here the power input to propeller is shown, while these two indicators show rudder position and boat speed. These two videos show visualization of predicted boat motion in a coordinate system moving with the boat on the left and in a laboratory coordinate system on the right. The boat is self-propelled and free-running, performing a particular maneuver. The power delivered to propeller is linearly increased to 3/4 and then held constant for a while. The speed varies because the resistance in wave varies, as seen on slide 24 for a container ship. When the rudder is turned to the starboard side, the boat starts turning right. The rudder is then quickly moved to a larger angle on the port side, and the boat turning slows down. The power is then increased to full capacity and the boat speed increases. The video on the right shows the trajectory of the boat in an Earth-fixed coordinate system. It is also possible to control the rudder position and power such that the boat travels the desired trajectory. Such simulations presently last a while, but with increasing computing speed of modern computers, they will become commonplace in design and optimization of vessels under realistic boundary conditions. Here is a summary of this lecture. Fluid flow and flying or floating bodies interact in both ways, that is, fluid flow affects body motion and body motion affects fluid flow. It is therefore desirable to solve the equations for linear and rotational motion of bodies together with the Navier-Stokes equations, that is, using discretization methods of the same order and the same loop for outer iterations within time steps. Under-relaxation of changes in body motion may be required, in a way similar to under-relaxation of changes in fluid velocities and pressure. The grid needs to be adapted to body motion in each outer iteration at each time step. The most general approach is to use overlapping grids, which is applicable to arbitrary motion, path crossing, and long distances. Other approaches, like moving the whole grid or individual regions as a rigid body and grid morphing, may be more efficient in some specific applications, for example in shallow water.